Hello, in this lecture, we are going to do a few more questions on electric field calculations. Basically, we were doing integral method of for calculating the electric field. And in this lecture also, we are going to continue with the same. However, uh, in a few lectures later, we are going to see something called as Gauss law, where we would develop an easier approach in order to find the electric field. Okay, so we've done till now a line of charge. We've done a non-conducting ring, a conducting ring. We have also calculated electric field on the axial point, where on axial point of the uniform axial point on the line of charge, where a non-uniform charge distribution uh, in linear fashion was given to us. Okay, and now in this lecture, we are going to do a few more varieties and things like those. Like, for example, now we are going to do electric field at the center of the hemisphere and such questions, so that you'll be able to understand a few more ways, a few more ways, and exposure to a few more questions would indeed help you in order to understand this particular concept of finding electric field via integral method. Okay, so this is the very prime method, and in there could be, as we'll go along, you'll also, as I told you, you'll be seeing something called as Gauss law. Okay, but today in this lecture we are going to derive electric field at the center of a hollow hemispherical cup, let's say. Okay, so we want to find electric field at the center of the hollow uh, hemispherical cup. Okay, so let me make a diagram so that it helps you out somehow. Okay, okay. So I think this is not going to help us. I thought it's going to help us, but okay. So let us make a hollow hemispherical cup. So I'm making a hollow hemispherical cup here. Okay, so this is my hollow hemispherical cup. Okay, and we want to find electric field at the center of it. So we want to find electric field at the center of it, and let us consider it to be uniformly charged. Let us let us consider that the shown hollow hemispherical cup is of, let's say, radius r, and it is uniformly charged. It is uniformly charged. So let us say that this is uniformly charged, and the surface charge density is given to be sigma. The surface charge density is given to be sigma. So how to go about these questions? So what I'll do now, I'm going to take, okay, now I'm going to take a small differential element, okay, a very small differential element. So let us say I am at angle theta, and I'm considering okay. So here it is d theta, and in this particular, you can say, if you can understand, this would look like a ring. Okay, so basically how it would look like, it would look like a ring. So basically this is on the hemisphere. This will look like this. Okay, so this will look like this. Okay, just for the sake of your understanding, I'm drawing it separate. Okay, so this is how it would be. Okay, now you see the case of ring we have done already. Okay, what would be the charge contained over this ring? Okay, so what would be the charge contained over this particular ring? So the charge contained over this ring would be simply sigma into ds. And what would be ds? So let's say this is theta. Okay, if this is theta, then this distance from the center can be simply written as r cos theta, and this radius can be written as r sin theta. Okay, so basically the ring that you are seeing here, it is of the radius r sin theta. Okay, so sigma into ds. And what would be ds? ds would be simply 2 into pi into this r sin theta. This is the circumference. So one of the length would be 2 pi r into sin theta. So 2 pi r sin theta would give you the circumference, and this width is simply r into d theta. So for some elemental area, you need two length elements. So one of the length element would be to consider the circumference, and another would be this width. So this width is r d theta. So this is the total charge dq contained over this particular ring. Okay, and we've already seen the formula for ring. On the axis of the ring, at a distance x, the electric field is given by kqx upon x square plus r square raised to power 3 by 2. Let us say this ring is containing charge q and of radius r. Then at a distance x, if one wants to calculate the electric field, then this would be kqx upon x square plus r square raised to power 3 by 2. So now instead of this ring, we have this ring. And if we calculate electric field at this particular point due to this ring, and if we try to integrate the contribution from each of the rings, like from here, then again if we take another ring from here, then we again take another ring from here, and if we keep on doing it, so basically we're going to take the contribution of the electric field from each of these rings, is then we will be actually covering the entire hemisphere. Okay, so in order to calculate electric field at c, so this is c. In order to calculate electric field at c, we will actually, what we'll do, we will actually uh, we will integrate all such elemental contribution to the electric field. So what will happen? So for example, because of this particular elemental ring, there would be some electric field here. Then you consider another ring from here, whose contribution to electric field you can find here. Then another ring from here, and all these small rings, elemental rings, you can keep on finding those electric fields, and keep on finding contribution at this particular center C, and effectively adding all these contribution is actually equivalent to integrating. So we'll integrate So what we'll integrate? We'll integrate the net electric field due to this particular ring. So what will be electric field? Electric field will be K. What is dq into distance x? So what is distance here? From here to here, the distance is simply r cos theta divided by x square. What is x? X is again distance. So this is simply r square cos square theta plus radius of the ring. So here the radius of the ring is simply r square sine square theta. So I'll write r square sine square theta raised to power 3 by 2. So k dq r cos theta. What is r cos theta? It is the distance of the ring from the center. Okay, so this is k dq r cos theta, and the the radius of this hemisphere is simply r sine not hemisphere, sorry. Radius of this particular ring is r sine theta. So square sine square theta plus r square cos square theta raised to power 3 by 2. So k dq, instead of x, I have written the distance as r cos theta. And instead of x, I have written r cos theta. Instead of r, I have written r sine theta, because this particular radius of this particular ring is r sine theta. And I'll integrate it from where to where. I want to take the contribution of each of these rings. So from 0 to pi by 2, it will cover all the possible rings. It will cover all the possible rings, okay? R sine theta. And then you have, okay, dq. Now you see, I will write what? I will simply write dq as this. So k r cos theta. So I'll write sigma 2 pi r square sine theta. And then another r is here. So I'll write r cube sine theta cos theta d theta divided by r cube only, because r square cos square theta plus r square sine square theta is r square raised to power 3 by 2 will give you cube. So this gets cancelled. Now you see this integration. Let us calculate this integration. I think why this r is here, I don't know. K dq now. K dq. This r should not be here. Sorry. This r should not be here. So I think this will be k sigma 2 pi okay, a sigma 2 pi, and this sine theta cosine theta, I think I can write it as sine 2 theta d theta and this 2 I'll absorb from 0 to pi by 2. What is integration sine to theta? The uh, sine to theta, integration sine to theta would be simply cos 2 theta by 2 minus cos 2 theta by 2. So k sigma pi minus cos 2 theta by 2. And instead of writing minus, I will just change the integral limits. So eventually it will be equals to k sigma pi. Cos 0 is 1. Cos pi is minus 1. So 1 plus 1 upon 2. So you'll get simply 1. And this will be equivalent to writing sigma upon 4 epsilon naught. So this will be the electric field at the center of the uniformly charged hemisphere. Okay, so I hope you might have got this particular approach. And if there is certain doubt, kindly let me know in the comment section.